All right, hello everyone, and welcome to 11.1 Part 2. And so what we're going to do in this lesson is use some of the knowledge that we learned in the previous day and start to really kind of put it together and formalize the hypothesis test that you would run, or what the AP test would actually test you on, or the questions they would ask you. So let's go back, and if you haven't already done so, record the information from the previous lesson. And so these were all the observed values. We didn't actually observe them. This is old data that I used, and what we expected to get using the same sample size of 348. So just to kind of remind us, we got these expected by going 13% of 348 is 45.2. 14% of 348 is 48.7, and so on for all the rest of those colors. We got our test statistic of 21.7 by doing all of the observed minus expected squared over expected, and we got the sum of all of those, and that's where that's coming in right there. So whenever we're running these tests, these procedures, you always have to check to make sure that the conditions are true, or that they are satisfied, I should say. And the two conditions, the only two conditions we care about now, notice before we'd always go random, independent, and then check to see if it was normal. We're now going to check to see if it is random, and then we're checking to see if our expected counts are all greater than 5. We have to have enough expected values, or our expected values have to be large enough for us to say that, hey, you know what, this is an okay thing for us to run. We're not checking to see if it's normal. We're not checking to see if our data looks like this. What we're actually just checking to see is, do we have enough expected values? And we're not checking to see if it's normal because, well, if you look at the chi-square distribution, it's really not normal right here. It really looks more like a skewed right distribution. And the reason for that is most of our data should really be kind of right around 0. Like what we expect and what we're observing should, for the most part, be close. But then once you start getting like really far away, then you have larger chi-squared test statistics, and that's when we start saying, the claim distribution is not true, or all of those different things. So checking the conditions, random. Well, we didn't do this as a class, but the M&Ms were randomly sampled. M&Ms were randomly sampled. And then for the large counts, all that you do is you say, find your lowest expected value. And for us, we actually have 2 in this case. That's not usually true, but for this example, we have 2. So you start off by saying lowest expected value. You're going to say brown and red are equal to 45.2, which is greater than 5. So 45.2 is our lowest expected value. That's greater than 5. So therefore, all expected counts or values are greater than 5. And so this is the format that you're going to need to have every single time you do this. You start off with the lowest expected value is greater than 5, therefore all expected are greater than 5. You could really go through and you could just check all of them. You could say 45 is greater than 5, 48.7 is greater than 5, 69.6 is greater than 5, 55.7 is greater, 83.5 is greater than 5, and so on. You can do that. It's just going to take more time as we add categories. So you start off, to save you time, you just do the lowest is this, greater than 5, therefore all are greater than 5. So calculating the p-value, so our degrees of freedom is 6 minus 1, because it's the number of categories minus 1, so we get 5 for that. Our test statistic we already found is 21.7. This is our chi-square. And then we want to use table C to find that p-value. And from the previous lesson, we said that our p-value would be somewhere between these two numbers here. So our p-value is about 0.0015. So 0.0015. And again, that's just really an estimate. It's not the exact, but it's enough for us to make the conclusion. So make a conclusion using alpha is equal to 0.05. Excuse me. Well, let's use the same format that we always do. So you'd say, because the p-value is approximately 0.0015, which is much less than this alpha significance level of 0.05. So because of this link to the p-value, we're able to then reject our null. And you would then say we have sufficient evidence to suggest that the claimed M&M color distribution is not true. And so this is just to sort of piece it together. We are saying that the p-value is less than alpha, less than or equal to alpha, which allows us to reject our HO. And then we're going to say, so we're rejecting HO, so we have evidence for HA. But instead of just saying for HA, we have to make sure we add in that context to get all of the points for our conclusion. So p-value is less than alpha, we reject HO, we have sufficient evidence to suggest that the claimed M&M color distribution is not true, and that is our HA. And so which M&M had an observed value that was the farthest from the expected? Well, if you go up to here, you would have to just look which observed and expected were the farthest away, and that would be probably this blue right here. This blue, and if I go up a previous page or two, I could see exactly what their observed values are, and it's showing that the blue, yep. So blue is about 800 or I'm sorry, the observed and expected. The blue is about 29 away, observed and expected, and that's much larger than the next highest, which is about 18. So we're going to go with blue there for the answer to this question. So blue was about 29.5 lower than we expected. Okay, so now what I want you to do here, let's flip the page. I want you to formally complete this hypothesis test. So, do the data provide significant evidence that the company was lying about the distribution of colors of M&Ms? I want you to pause the video here and complete this entire page, and then we will come back together in just a second. Okay, so I've gone ahead and completed this page. Let's go ahead and check that yours is the same. So our hypotheses are HO and our HA. Our HO is the claimed color distribution is true. Our HA is the claimed color distribution is not true. We're getting the context in there by talking about the color there. The significance level is the alpha equals 5%. I know this up here says A equals 5%. My word processor messed it up when it was converting it to a PDF. It should be alpha equals 5%. The name of the procedure is given to us right here as the chi-square test for goodness of fit, or it can be shortened to the chi-square goodness of fit test, just like that. And we're going to learn about two additional chi-square tests after this. So the conditions, random. Well, the M&Ms were randomly sampled by my class last year. And for large counts, we would just check that the lowest expected value is greater than 5, which we found is true for brown and for red, for brown and red. Therefore, all expected are going to be greater than 5. The picture, well, we have a chi-square distribution, so it better not look normal. It's got to be skewed to the right with a degrees of freedom of 5, and so that's what this chi-square 5 is right there. We would have for a z distribution, we do normal with mean and standard deviation. For a t, it's t degrees of freedom, and for the chi-squared, it is chi-square degrees of freedom, just like that. Notice that the specific formula right here actually looks like what we would typically have is the general formula. Well, lucky for us, the chi-square tests all use the same formula. So the specific formula is the same for all of them. It's just the sum of the observed minus the expected squared over the expected, which again is given to us on the AP Stats formula sheet up here at the very top, first page, the chi-square test statistic right here. So the observed value minus the expected over the expected once you square it, plus all of them, and then the observed minus the expected squared over the expected. And something to just note is both of these expected are the same, which is very uncommon. These should all really be different numbers, so don't get that confused. It's just that for brown and red, that are both the first and the last, they just happen to have the same expected. But the next one would be 47 minus 48.7 squared over 48.7 plus 88 minus 69.6 squared divided by 69.6. 74 minus 55.7 squared divided by 55.7, and so on, like that. So we end up with our chi-square test statistic that we found last time of 21.7. We then find the p-value by going to table D with the degrees of freedom of 5, and we found that our p-value is about 0.0015. And so then we can conclude that because the p-value is less than alpha, we reject Ho. We have convincing evidence that the claimed M&M color distribution is not true. And just like a little follow-up to see if you noticed anything that was missing, but what parts of the four-step process are missing, and that would be, well, we don't have a parameter in this case. We don't have like a mu is the true mean, blah, 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 or p is the true proportion of blah, blah, blah. Instead, we're just trying to find is what they're claiming, the percent of brown M&Ms, is that true? Is the percent of yellow, is that true? So the chi-square is really just finding, the farther away these observed values are, the higher or the larger our chi-square test statistic will be in this case. So we don't have a parameter, we don't have a statistic, we don't have a general formula because the general and the specific are really the same. And that leads us to our learning targets. So, learning targets. Start off with this. Zoom in a bit. So the first LT that we will be talking about is the conditions. LT number 1. That is the conditions. Conditions. So the first condition that you need to check is it random? And the second is large counts. A little different than the large counts that we've been doing, where it's NP greater than or equal to 10, NP greater than or equal to 10, and then we check N1 minus P greater than or equal to 10. I mean, we're still doing the first part of this, the NP, but now we're changing it just to 5 rather than 10. And we're having to check this really for all of the categories that we have. And so we know N times P is just the expected value. So what we're really saying is, first we check that the lowest expected is greater than 5. So all expected are greater than 5. So you have to actually check this one here, and then you can just sort of state this sentence on the bottom. Next, learning target number 2. Learning target number 2. That would be the chi-squared distribution. So as a picture, you can have it drawn kind of like a nice right skewed mountain. 0 at the beginning. You have your chi-squared with degrees of freedom. A couple things to note for possible multiple choice questions in the future would be that this is always skewed right. And it will always also start at 0. Okay. And the final learning target will be the 4-step process and some follow-up. So LT number 3. So 4 steps. 4 steps and follow-up. So a little follow-up to make sure that you get maybe a roundup if you're ever in those in-between scores. So you have the state, still the plan, the do, and the conclude. Let's see. So if you ever end up with a significant result, or I'll say it as if you reject your hoe, let's put this in a different color. If you reject hoe, it's also good to follow up with discussing which value was the largest contributor to the chi-squared. So discuss or just mention which value, or which, I should say, maybe which category was the largest contributor to the chi-square value. And so that's what we did right here, kind of at the very end of I really should do it right here. But let's take a look at what we did at the bottom of the first page. So which M&M color, this question 5, which M&M color had an observed value that was the farthest from the expected value? So that was, we said, was blue. And what we're really saying there is that blue, I'm just scrolling up to take a look, blue was the largest contributor of this chi-squared. You can see 10.4 of the chi-square is 21.7. 10.4 of that came from blue. And so blue really is the biggest reason for it being so large. And so just mentioning that at the end is a great way to show the readers or the graders that you know what's going on. So I'll finish this up with blue was the largest contributor to the chi-square value. Just a nice follow-up at the end of our hypotheses like that. Okay, so now what I want you to do is pause the video here and work through this next check your understanding, and then unpause once you've completed it. Okay, so does this data provide convincing evidence that the distribution of car color in Oro Valley differs from the North American distribution? So my hypotheses are that the distribution in Oro Valley is the same as the North American distribution. Just notice that I shortened it to NA distribution. And then our ha would be that the distribution in Oro Valley is not the same as the North American distribution. So the conditions that we are checking, random and having a large enough amount of expected counts. So for random, we would say that the random or we quote that the random sample of 300, and that comes right out of the question right here, random sample of 300. And for large counts, we would say the lowest expected count is 300 times 0.07. Or you know what, actually, there is one that is smaller than that. So that wasn't a great one right there. So the smallest would really be this 2% one right there. So 300 times 0.02, and then that's going to be 6. But 6 is still greater than 5, so we're still good there. And so because our smallest expected value of 6 is passes the test, we know all of the remaining will be greater than 5. And this is, again, a chi-squared goodness of fit test, or you can shorten it to a chi-squared GOF test. So the work. So our specific formula from the formula sheet, chi-square is equal to the sum of the observed minus the expected squared over the expected. This is an easy one to write down. You don't have to remember any real specifics from this. This just comes right off that formula sheet. So let's plug in our work. So 84 is the first observed value, is 84 right here, minus the expected, which is 69. Well, where does that 69 come from? Well, what that is it's that 0.23 times the total number of cars in the sample, which is 300. So 23% of 300 is 69. And so 84 minus 69 squared over 69 plus, you would then do 38 minus the expected, blah, 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 all the way until the end, which is 39 minus 21 squared over 21. And again, that 21 is coming out of what we expect, 0.07 times 300, which gets you 21. So we end up with the chi-square test statistic of 29.92. Going to table D, we find that our p-value is less than 0.0005. So super tiny, super tiny, meaning we were very far from what we expected. So that gives us evidence to suggest ha. So what we say is, because the p-value is approximately 0, which is less than 5%, we reject ho. We have convincing evidence to suggest the distribution in Oro Valley is not the same as the North American distribution. And because we rejected ho, so because we rejected ho, we then want to have this follow-up. If we didn't reject ho, we wouldn't have this follow-up. But because we rejected ho, we would then want to follow up with, even if this question wasn't here. So this is kind of to try to help us in the notes. But on an exam or on the homeworks, you want to follow up regardless of if this question is there or not. We would say that the largest contributor to the chi-squared value was from the other category. So from where is other, from this other category here, where we were actually 18 away from what we expected. So we observed 18 different than what we expected.